Great. So I think it's 3 p.m. German time. So it's my great pleasure to welcome you all to our SPICE-SPIN+X seminar series. And as many of you know, this is a series which is jointly organized by Jairo Zinova and Karin Everschotter from the Spintronics Interdisciplinary Center and the Collaborative Research Center SPIN+X, which is jointly run by Martin Eschliman and Burkhard Hillebrand, as well as myself. So this is a webinar format. So when you join, you can watch. And if you have any questions, please put your questions in the chat and I will read them out later. Or if you have a question you'd like to ask in person, you're welcome to raise your hand. And then I will promote you to speaker, and then you can unmute yourself and ask your question. So we do this every Wednesday at 3 p.m. Here you can actually see the people that there's a lineup for the next couple of weeks. So we have the Alexander Mook from the University of Basel next week, and then Benedetta Flebus from Boston College the week after. And then there's the conference, the TMAC conference. We're going to have a break in between over the August. We will have, I think, 4 weeks of no seminars. Yes, and now without further ado, it's my great pleasure to introduce our speaker today. That's Professor Shunsuke Fukami from Toku Daigaku, from Toku University. And as we've just been discussing, so he comes from Aichi Prefecture. He studied at Nagoya University and then also continued to do a PhD at Nagoya University. And many of you will probably know him from his large body of work. He's been very active in various aspects of spintronics. In particular, I know him from the spin orbit torque community, but also from TMR and non-conventional computing at the forefront of both condensed matter physics as well as computer science and electrical engineering. And he has a number of honors and awards, which include the Young Scientist Presentation Award from the Japanese MEXT, the Asian Union of Magnetic Societies Award, the Young Researcher Award, and the Outstanding Researcher Award of the Magnetic Society of Japan, and the outstanding paper awards as well. And yeah, so we're very much looking forward to some exciting insights. And so I'll hand over to Shunsuke. So the floor is yours, please.
Okay. Okay, I will start. Okay, so can I start?
Yes, go ahead, please. Okay. Looks good, sounds good.
Oh, okay, so thank you, Matthias, for introductions. I'm very happy to have this wonderful opportunity. So I'd like to thank the organizers, Jairo, Matthias, and other colleagues. So the title of my today's my talk is Electrical Manipulation of Non-Collinear Antiferromagnet. And this work was mainly, so the most of the experimental part was done by Yutaro Takeuchi in our laboratories, and the calculation was done by Yuta Yamane, who was in actually Mainz a few years ago. So who was a member of Jairo's team a few years ago. Okay, so let me start. Okay, so the electrical manipulation of magnetic material is the main focus of my today's talk. So first, I'd like to give a brief overview on the demonstration of the representative scheme of the electrical manipulation of magnetic materials demonstrated in the past about 20 years. And after that, the non-collinear antiferromagnet is the main player in my today's talk. So I'd like to also give a brief introduction to these material systems. And in the second part, it's the main part of my talk. So I will show a chiral spin rotation observed in a non-collinear antiferromagnet manganese-3 tin. So I will first describe preparation of epitaxial heterostructures consisting of a manganese-3 tin, and then I will show the experimental results of the chiral spin rotations. And I will also describe the domain size, and also I'd like to show some results of the manganese-3 tin thickness dependence of the threshold current to induce the chiral spin rotations. And finally, I will summarize my talk. Okay, so let me start from the introductions. So the electrical manipulation of magnetic materials. So this is the summary of the representative schemes of the electrical manipulation of magnetic materials. So there are several phenomena that have been observed in various material systems. So let's have a look at the collinear ferromagnetic systems first. Okay, so as most of you know, the current can induce the magnetization reversal. And this was firstly observed by Cornell's teams in 1999. So the spin transfer torque induced magnetization switching. So they used CPPGMR structures, cobalt, copper, cobalt, and they pass current through this GMR device, and they observed bidirectional magnetization switching, as shown here. So this can be clearly used for non-volatile memory devices, and there tremendous efforts has been devoted to realize a non-volatile device. And there are many important discoveries. And one of the important discoveries is that perpendicular easy access cobalt ion boron MgO-based magnetic tunnel junctions. And the importance of the discovery of this material system is that this system can satisfy major requirements, such like the small switching current and large TMR ratio and large good retention properties. And very recently, as you know, the spin transfer torque MRAM has been commercialized. And by the way, this is the microscopy image of the recently commercialized chips by Sony, and they used STT-MRAM as the buffer memory of the CMOS image sensor. Sorry, I'm not sure this is commercialized, but they presented the STT-MRAM as a buffer memory of the CMOS image sensors. And also, so this is different from the spin transfer torque induced magnetization switching, but the spin transfer torque can also drive the move the domain walls, and so this is a famous work by Tohok team and Teruo Ono's team, and Matthias also did a wonderful works regarding the current induced main wall motion, and the race track memory was proposed that can, in principle, realize very large class storage memories. And about 10 years later, from the spin transfer torque induced magnetization switching, the spin orbit torque was also found to induce the magnetization switching. And by the way, recently, review paper was published in which I am also one of many co-authors. So I think that this paper is can serve as a dictionary of the spin orbit torque related phenomena. So please have a look at this paper if you have an interest. Okay, and next phenomena is the magnetic phase transitions. So in 2000, Hideo Ono and his colleague demonstrated that the electric field can induce the phase transition of the ferromagnetism. So because so they use magnetic semiconductors, and these material systems exhibit the ferromagnetism due to the and the ferromagnetism originates from the hole. So by tuning the concentration of the hole, they can control the ferromagnetism. And indeed, they apply the negative voltage and induce the ferromagnetism. And by applying the positive voltage, they switch to the paramagnetic state. So the electric field can modulate several magnetic properties. And indeed, a few years later, the same team demonstrated that the electric field can modulate the magnetic anisotropies, and the coercive field was changed by the electric field. And the same phenomenon was observed in the metallic systems, and also in metallic systems, the magnetic phase transition was observed. And in 2012, using the electric field induced anisotropy, the dynamical switching was demonstrated, in which when you apply the electric field, you can change the magnetic anisotropies and induce the precessions. And so if you can turn off the current at the specific timing, you can switch your magnetization. So this is the electric field induced magnetization switching. Okay, and the third example is the oscillation or resonance. So again, the Cornell team demonstrated that the DC current can induce the stationary oscillations, and emit the RF signals at the specific magnetic field. And also the inverse process was observed by Osaka University team, and they apply RF current, and then through the ferromagnetic resonance, the DC signal was observed at the specific frequency, at the specific magnetic field. And also in 2005, the phase locking between the two oscillators was observed almost the same timing. And this is very important because the phase locking or the synchronization can be used as the promising phenomena for the computations. And indeed, recently, the neuromorphic computing based on the synchronization of the oscillator was demonstrated. And also, this is just an advertisement, but our team and Hyun-Soo Yan's team in the National University of Singapore demonstrated that communication and the energy harvesting using the spin-torque oscillator arrays. And we demonstrated that the spin, by carefully tuning the magnetic tunnel junctions, the spin-torque oscillator arrays can emit or receive the electromagnetic wave whose frequency is 2.4 gigahertz, which is the frequency of the Wi-Fi signal. And also, we demonstrated that the spin-torque oscillator array can receive the electromagnetic wave of the Wi-Fi signal and generate electric power that can turn on the LED. So this can be also used for as the energy harvesting technique. Okay, so let's I'd like to emphasize that the oscillation is observed in the specific when you apply the magnetic field. Okay, so let's return to this page. And so what I'd like to say is that the many interesting phenomena was observed, and that has led to important applications in the ferromagnetic systems. Okay, so let's now move on to the collinear antiferromagnet. So I think most of you knows well, the Néel vector rotation in the copper manganese arsenides was observed in 2016 by Pete Wadley and his colleague. So the point is that they utilize the spin orbit interactions. So that if you use a magnetic field, you cannot manipulate the Néel vector, but by using the spin orbit interactions, you can individually control the sublattice of the antiferromagnet, and indeed they can rotate the Néel vector by 90 degrees. And the same phenomena was observed in manganese to gold by Matthias's team and Marcus and his colleague. And also the Chen Song and his colleague also observed the same phenomena in manganese to gold. And they studied two systems. One is simply the manganese to gold, and they also studied the system with platinum capping, and the similar phenomena was observed by using the spin Hall effect of the platinum manganese. And the same phenomena was observed in the nickel oxide, and our team also recently presented that the similar phenomena was observed in the polycrystalline platinum manganese. Okay, so now let's go to the main part. So the, today I'd like to talk about the electrical manipulation of non-collinear antiferromagnet. Okay, so the non-collinear antiferromagnet, that is a very interesting system because it can behave like ferromagnet despite negligible magnetization. And theoretically, Professor Alan McDonald's team and the Claudia Felser's team predicted that the large anomalous Hall effect was observed due to the non-vanishing Berry curvatures in manganese-3 iridium or manganese-3 germanium or manganese-3 tin. And indeed, in 2015, Professor Nakatsuji and Stuart Perkins' team observed the large anomalous Hall effect in diesel 90 manganese-3 tin and or the manganese-3 germanium. So the large anomalous Hall effect is observed due to the non-vanishing Berry curvatures. And in a similar way, the anomalous Nerunst effect and also the magneto-optical Kerr effect was also observed in the non-collinear antiferromagnet. And so this is also Nakatsuji-san's team's work, and this is the Jörg Underlich's team's work. Okay, and this is also from the Professor Nakatsuji's team. Okay, and very recently, the electrical manipulation of the non-collinear antiferromagnet was reported in these papers. So they prepared bilayer structures consisting of a polycrystalline manganese-3 tin and platinum, and they apply a current in these directions. And so when they apply the magnetic field along the X directions, the magnetization switching, the switching of the Hall voltage is observed. And when they replace the platinum by copper, nothing is observed. But when they replace platinum by tungsten, the opposite behavior was observed. And they also studied the external field HX dependence. And so as you can see, the switching direction becomes opposite by changing the sign of the sign of the external field. So this is very similar to the spin orbit torque-induced magnetization switching, and they perform the theoretical, they give the theoretical discussions, and according to the explanations, the octapole moment behaves as like the magnetization in the ferromagnet, and the octapole moment switches with the same protocol as the spin orbit torque-induced magnetization switching. So the question is that this is very similar to the ferromagnetic systems. So the question is that are there any characteristic phenomena in the non-collinear antiferromagnet? And the answer is actually yes. And actually, so I didn't know the paper until very recently, but the Helen predicted a very interesting phenomenon in 2015. So she studied the dynamics of the chiral spin structures in L12 manganese-3 iridium. So she studied the Tori layers, the response of the chiral spin structures in this Tori layer structure consisting of the manganese-3 iridium, non-magnet, and ferromagnet. So the behavior of the chiral spin structures against the spin polarized electrons. And according to this paper, she mentioned that there exists a stationary state in which the antiferromagnetic vector rotate in the plane 111. So she derived this phase diagram, and in certain areas, the chiral spin rotation, chiral spin structure rotates in the clockwise or anti-clockwise directions at zero magnetic field. So this is clearly different from the ferromagnetic oscillations, because the rotation can be induced at zero magnetic field. So today I will show that the chiral spin rotation can be observed in the non-collinear antiferromagnet as Helen predicted. So okay, so now let me move on to the main part. Okay, so so the objective of this work is to observe the chiral spin rotations. So this is the schematics of the chiral spin rotations. So as you can see, each sublattice rotate as shown here, and the residual magnetic moment also rotates as shown here. So to observe this behavior, we need to prepare epitaxial structures in which the Kagome lattice can be controlled with respect to the injected electron spins. So we first try to prepare the epitaxial heterostructures. Okay, so first I'd like to describe the preparation of the epitaxial bilayer structures. Okay, so this shows the stack structures we studied. So we used MgO110 substrate, and we tried several underlayer materials to grow the manganese-3 tin. And so we when we deposit this film, we heat the stage to up to 400 degrees Celsius. And after that, we also anneal the samples at high temperatures. And to characterize the crystalline structures, we mainly use XRD, and also we use VSM and PTMS to evaluate the magnetic and magnet transport properties. Let me show the structural characterization by XRD. So, making long story short, we found that the tungsten is very promising materials due to the small lattice mismatch between the with the manganese-3 tin. But if we simply use a tungsten underlayer without tantrum, we observed unfavorable peaks, which indicates the formation of tungsten manganese 2 tin. So this is unfavorable. So we inserted a tantrum, and by increasing the thickness of the tantrum to thicker than 1 nanometer, this alloy peak disappears, and we just observed the favorable manganese-3 tin peak. And so, by the way, this manganese-3 tin 1 bar 00 peak indicates the presence of the D090 ordered phase. So, as shown here, the D090 manganese-3 tin has been successfully prepared. And this shows the phi scan results. and this, from the phi scan results, the epitaxial relation was identified as shown here. So the MGO110 direction is, the MGO001 direction is the manganese splitting 0001 direction is formed in the parallel direction to the 001 axis of the MGO substrate. Okay, and this shows the cross-sectional TEM image of the M-plane oriented samples. So this shows the low magnification image, and so you can see the MGO substrate, tungsten tantrum, and diesel-90 manganese 13. And this shows the magnified image, so high resolution image. So you can see that the dark hexagonal spot are surrounded by the brown, bright hexagonal spot, which is nothing but the ordered structure of the diesel-90 manganese, the 0001 plane of the manganese 13, or the Kagome plane of the manganese 13. So the very nice epitaxial thin film was formed by this stack structures. Okay, so next, let me show the magnetic and magnet transport properties. So so this shows the MH loops measured by the BSM. So we see a very small residual magnetization of around 5 milliteslas, but we observed a very large anomalous hole conductivity up to 13 ohm centimeter inverse when we annealed the sample above 550 degrees Celsius. Okay, so we now have the nice epitaxial thin film. So next we prepared the device to observe the chiral spin rotations. Okay, so this shows the stack structure we used to observe the chiral spin rotations, and this shows the optical micrography image of the fabricated device with the measurement circuit. So we prepared a whole bar device in which the channel width was varied from 3 micrometer to 50 micrometers, and the channel length and the width of the whole probe was fixed to 50 micrometer and 3 micrometer respectively. And this shows the whole resistance as a function of the magnetic field, which was applied along the perpendicular out of plane directions for the manganese thickness of 8.3 nanometer. So very nice negative and square RH loop was observed, which means that the anomalous Hall effect due to the chiral spin structure is observed. And the point is that even in a very thin 8.3 nanometer manganese 13, this chiral spin structure is formed in our stack. And also in this experiment, we capped the manganese 13 by platinum. So as you know, the tungsten, tantrum, and platinum has the opposite spin hole angle. So with these stack structures, we can expect that the large enhanced spin orbit torque can be exerted on the manganese 13. And we also prepared an MGO capped sample as a reference to examine the effect of the spin orbit torque. Okay, and we studied 2 configurations. So this is the first configuration in which the Kagome plane is expected to be perpendicular to the accumulated spin, whereas this is shows the second configuration in which the accumulated spin is is in the Kagome planes. Okay, so we compare these to the results observed in these 2 configurations. Okay, so let me show the main results. So we first studied this configuration. So the spin is perpendicular to the Kagome planes. So this is the first results. So we first initialize the chiral spin structures by applying a strong magnetic field. So this is the starting point. And we first sweep the current to plus directions. Then at a specific current, it go to the intermediate level and fluctuate. And when we reduce the current, it follows the same way. And below a specific current, the fluctuation stops. But when we go to the negative directions, the fluctuation again starts and return to zero, then the fluctuation stops. Okay. So next we change the sweep direction of the current, and the similar behavior was observed. And when we change the initialization directions, the similar results was observed. So next, in the next configuration, the result is as shown here. So in this case, the results are qualitatively the same, but the threshold current to change the state is different by about a factor of 10. So the points are that the whole resistance transits to intermediate level regardless of the directions of initialization and current. And the threshold current is largely different between the two configurations. And also the fluctuation level of the whole resistance is largely different below and above the threshold current. Okay. So next we identify the driving force to induce this peculiar phenomenon. So first we change the cap layers by from platinum to MgO layer, MgO ruthenium. So as you know, the MgO is expected to generate the negligible spin orbit torque. So the much larger current is expected to be required to induce the characteristic response of the whole resistance. And indeed, the platinum capped sample shows a much smaller threshold current and threshold current density as shown here. So the red plot shows the results of the platinum capped sample. So it shows the smaller threshold current and threshold current densities. And next, we studied the RH loops under various DC current. So we measured RH loops for different DC current. And we plot the observed threshold coercive field as a function of the applied current for the two systems with different cap layers. And we observed a linear change in the coercive field, which means that the some current-induced effect modulates the coercive field. And so if the Joule heating is dominant, it is expected that the non-linear relation is observed, but the linear relation is observed. So this means that the current-induced effective field should be dominant for this observation. And finally, we also evaluate the Joule heating. So we first measured the channel resistance as a function of the temperatures. And after that, we measured the channel resistance as a function of the DC current. And results is shown here. So at the current of below 10 milliamps, the increase of the whole resistance is less than around 10 degrees Celsius. So we can say that the Joule heating plays a negligible role. So these results suggest that the spin orbit torque plays a dominant contributions. Then, so what is happening in, so what is a possible scenario for this peculiar phenomena? So our conclusion is as follows. So the chiral spin structure starts with the uniform state by the initialization by the magnetic field. And the whole cross consists of multiple magnetic domains, and the chiral spin structure in each domain starts rotating above the critical current. So when you turn off the current, each domain settles into one of the six stable points randomly. So as a result, because the whole cross has several domains, so that finally observed whole resistance should be an average of each domain. So so when we apply a current above a threshold, each domain shows the chiral spin rotations, and when the current is turned off, each domain settles into one of the six stable points. So that we observe the ensemble of the, each domain. So this is our conclusions. So to confirm this scenario, we performed a theoretical calculations. So this shows that so this page shows the calculation framework. So we used LLG equations in which the three magnetic moments in each sublattice are simultaneously calculated using this LLG equations. And the effective field was calculated from the derivative of the energy. And the energy is energy consists of three terms. The first term is the exchange interactions, and the second term is the Jaroszynski-Morier interactions, and the third term is the magnetic anisotropies in each sublattice. And for this work, we chose these parameters to reproduce our material systems. And this shows the calculation results. So the by the way, the residual magnetization for this assumption is 6 millitesla, which is very similar to our experimental systems. And this shows the dynamics of the residual magnetization as a function of time. So the as observed in the experiment, when the applied current is too small, nothing happens. But above a threshold, the oscillation is induced, and by increasing the applied current density, the speed of the oscillation also increases. And this shows the frequency of the oscillations as a function of the applied current densities. So below the threshold, nothing happens, but above the threshold, the frequency of the chiral spin rotation increases. So this means that this implies that this phenomena can be used for the tunable oscillators that can function at zero magnetic field, which is different from the spin torque oscillators. And also, we calculated this behavior as a function of the angle between the current and the Kagome lattice. So 0 degree means that the accumulated spin is perpendicular to the Kagome lattice, and the 90 degree means that the spin is accumulated spin is in the Kagome planes. So as you can see, the threshold current density increases with when the angle is it increases to 90 degrees. So this is also consistent with the experimental results. And we also studied the chiral spin reversal, which was demonstrated in the very recent Nature papers. So to observe the chiral spin reversal, we applied the magnetic field along the current direction for these configurations. And indeed, we observed the bidirectional switching when we applied the external field. And the switching direction reversed by changing the sign of the external field. So, and to compare these two results, our chiral spin rotations shows a continuous rotation of the chiral spin structures. And for this setup, the bipolar switching is observed. And this phenomena is observed at zero magnetic field, but this phenomena is observed only when the magnetic field is applied along the current directions. And also one more important thing is that the critical current densities are largely different. So this behavior was observed at the current density of around 1 megaamps per square centimeter, but this phenomenon was observed at the current density of around 10 megaamps per square centimeters. Okay, so these are the difference between the chiral spin rotation and the chiral spin reversal. Okay, so next I'd like to describe the analysis of the domain size. So as I mentioned, the fluctuation comes from the ensemble of the domains accommodated in the whole cloth. So we can expect that for wider wire, because the wider wire contains many dices, so the many domains should be accommodated in the wider wire. So the small hole resistance fluctuation should be observed. And for the narrower wire, because it contains a small domains, so the larger hole resistance fluctuation should be observed. So from the analysis of the fluctuation level, it is expected that we can estimate the mean domain size. So we did this experiment. So we changed the channel width from 3 micrometer to 50 micrometer, and we observed the fluctuation level for each devices. And as expected, the fluctuation level decreases with increasing the channel width. And we have to here care that the fluctuation should comes from the fluctuation of the chiral spin structure plus the measurement error. So we have to subtract the measurement error by these equations and determine the fluctuation level owing to the spin orbit torque. And this shows the main results. So the fluctuation level was normalized by the full scale of the hole resistance change, and we plot it as a function of the inverse of the square root of the cross area of the whole device. So as you can see, the linear relation was observed, and from the fitting, we could estimate the domain scale to be around 240 nanometers. And recently, the Chenson's team studied the width dependence of the coercive field, and they implied that they said that the coercive field decreases with decreasing the width, and it implies that the domain size dominates such behavior. And according to the explanation, the domain size is somewhere around a few hundred nanometers. So our result is consistent with their implications. Okay, so finally, I would like to describe the thickness dependence of the threshold current. Okay, so now let me introduce one interesting work done by Hyun-Soo Yang and Kyung-Jin Lee's team. So they studied the spin torque acting on the ferromagnet and antiferromagnet. And according to the theory, the spin diffusion length or spin coherence length can be given by these equations. So for the ferromagnet, because the wavelength for upspin and downspin is the same, so in ferromagnet, the spin torque is basically active only near the surface. But for the antiferromagnet, it should be active for the long range. So the spin torque for the antiferromagnet is like a bulk-like torque, which is different from the ferromagnet. And they carried out an experiment. So they prepared two systems. One system has the ferromagnetic cobalt nickel, and the other system has the antiferromagnetically coupled cobalt tellurium multilayers, which was capped by platinum. And indeed, the switching efficiency, which is defined as the L-step. So the switching efficiency is the coercive field divided by the threshold current density. It decreases with increasing the thickness of the ferromagnetic layers for the ferromagnetic systems, but it increases for the ferrimagnetic systems. And also the magnitude of the efficiency is much larger for the ferrimagnetic systems. So with this result, we conclude that the spin torque acting on the antiferromagnet is much efficient and is qualitatively different from the torque acting on the ferromagnet. So the question is, how about in non-collinear antiferromagnet? So we studied it, and we prepared several structures with different thickness of the manganese tin, and we measured the coercive field and the critical current density as a function of the thickness of the manganese tin, and we plot the coercive field divided by the threshold current density as a function of the thickness of the manganese tin. And the obtained results are plotted by the star symbols. So as you can see, for the non-collinear antiferromagnet, the results follows the 1/T relations. But the more interesting thing is that the efficiency is much larger than the ferromagnetic systems and collinear ferrimagnetic systems. So at the last of my talk, I'd like to discuss why the spin torque on the non-collinear antiferromagnet is so efficient. So actually, we have not reached a solid conclusion, but we think that for the field-driven dynamics, the out of Kagome plane anisotropy governs the threshold field or the coercive field, and also the small net magnetization results in a large anisotropy field and resulting in a large coercive field. But for the current-driven dynamics, it is mainly governed by the in Kagome plane anisotropy, as shown here. So for the field-driven case, the each moment in each sublattice should rotate out of the Kagome plane. So that out of the Kagome plane anisotropy determines the threshold field. But for the current-driven case, the in Kagome plane anisotropy basically determines the threshold current density. So because of the difference in the two anisotropies, the non-collinear antiferromagnetic systems shows a much efficient current, shows the much efficient manipulation of the magnetic moment. Okay, so with that, let me summarize my talk. So I first described that about the epitaxial M-plane oriented manganese 3 thin films, and we prepared the epitaxial systems on the MgO substrate with the tungsten tantalum buffer layers. And then I described the chiral spin rotations. So I showed that the hole resistance transit and fluctuates above threshold current density. And the threshold current depends on the Kagome plane orientations. And these results can be consistently explained by the chiral spin rotation induced by the spin orbit torque. And the chiral spin rotation requires no field and smaller current compared with the chiral spin reversal. And the domain size was estimated as 240 nanometer from the fluctuation level versus the wire width. And I also described that the chiral spin rotation shows higher efficiency, switching efficiency than the collinear systems. Okay, that's all. Thank you for your attention.
Okay, thanks a lot. So this is a very exciting talk. Now what we're going to do is, if you raise your hand, I will promote you to a discussion participant, and then you can unmute yourself. So the first person who's raised his hand is Helen. Yes. So then, Helen, you can unmute yourself and ask your question.
Can you hear me?
Yes.
Yes.
Thanks a lot for this interesting talk, and I'm very happy that experimentalists can realize this. It's fantastic. So what I learned from the ferromagnetic spin-induced dynamics is that there is a hysteresis when for threshold currents when you go up and down. So the threshold current for setting rotations is larger than the current for stopping rotations. At least this is predicted by theory for collinear antiferromagnets. So have you tried or have you seen this kind of hysteresis?
So are you talking about this slide?
Yes and no. So I mean, hysteresis is not in the magnetic field, but so I do not know how you apply, how you change current in the experiment. Do you change smoothly current from 0 to higher values, or you apply some current pulses for each current value which you show on your graph?
We applied a pulsed current. So we apply pulse current and turn off the current and measure the whole resistance. And then we apply the second pulse with different magnitude and measure the whole resistance.
Okay. Because what I mean is a kind of experiment when you apply, so theoretically you can rise your current smoothly from small values to higher values and then return back. And then you can have this hysteresis in the dynamics. So to set rotation into motion needs more energy than to stop it.
Okay, thank you very much. So thank you very much for the suggestion. So we can try it. So we will try it.
Then you can make a memory element on this.
Okay. Thank you very much.
Okay, Mr. Rajan has two questions.
Yeah, so
go ahead.
Yeah, thanks, Professor Fukami. I have two questions. So firstly, do you expect similar switching mechanisms in cubic systems like manganese 3 nickel nitride?
I think so. So as far as you can inject the spin polarized, you can inject the spin current in perpendicular to the non-collinear spin structures. I think you can also observe the chiral spin rotations.
Okay.
So the point is that the configuration. So the accumulated spin should be perpendicular to the non-collinear plane.
Okay. So if we take into consideration the Kagome plane, then it should you would expect similar behavior.
Yeah, and also yeah. So my first answer is yes to your question is yes, but it also depends on the detailed parameters, material parameters. So it depends on the J0, D, and K.
Okay. And also whether applying mechanical strain would assist in the switching, or would it be would it not help? Because it
So I don't know, but so the switching current depends on the material parameters. So if you can change the material parameters to the better directions, the threshold current should decreases.
Okay. Okay, thank you.
So in particular, if the anisotropy goes down, then I guess the threshold goes down.
Yes, I think so.
Okay, so Mr. Gupta, Rahul Gupta, I think you can unmute yourself.
Hello, can you hear me?
Yes.
Yes.
My question is related to ruthenium 1 nanometer capping layer on top of your heterostructure. What is the purpose of that?
Well, this is just to protect the MGO. So this is just a protection layer. So there's no specific meaning, I think.
Thank you.
Okay, Jin Young. I mean, MGO is hygroscopic, so it has a finite lifetime. Okay, so Jin Young.
Hi, sorry, can you hear me okay?
Yes.
Yes.
Great, thanks for the great talk. So I had just a quick question about the domain sizes. So the domain size that you obtain from the whole cross the dimension, does that number correlate to the possibly from the what you can get from either XRD or the TM images? That was my first question.
Sorry, so the domain size, the relation between the estimated domain size and
the structural domain size from the XRD or the TM.
Structural domain size means the crystalline grain size?
Yes, yeah. Is there any correlation?
We didn't carefully examine it, but I think there should be no strong correlation.
Okay, with the
but no, it's not clear.
Okay. So then the second question is, so I saw, I think in the first part where you had a different annealing condition for the manganese tin films, and I was wondering then does the domain size change depending on the annealing condition? And I saw the anomalous Hall effect was small for the lower temperature annealing, and I was wondering whether that's also the effect to this structural or the magnetic domain sizes. I was wondering whether there any
I think that's a good point, and we didn't examine it, but I guess that the domain size should change with the annealing temperature.
Okay, thank you.
Okay, so before Dong-Wook asks, maybe I have a follow-up, Shunsuke. So if the 240 nanometers does not depend on some structural length scale, what sets the domain size then?
Yeah, actually, that's a very interesting point, because for the ferromagnetic systems, the domain size should be determined by the competition between the exchange and the magnetostatic
bipolar,
energy. But for the antiferromagnet, there should be no bipolar field. So that's a very interesting issue, and we would like to clarify it.
So Helen always tries to convince me it's magnetoelastic coupling due to structural defects. So maybe there is some structure in the size of the. Some
Yes,
crystallizers.
yes.
Okay. Okay, Helen, now I'm going to mute you before you start because we have more questions. But yes, okay, we can discuss that maybe offline. So Dongwook, please go ahead.
Thank you very much for an interesting talk. My name is Dongwook Go. Can you hear me?
Yes.
Okay, I have a question regarding the spin absorption in the non-collinear ferromagnet as compared to spin absorption happening in ferromagnet. For example, in the ferromagnet, I think there is a very nice, good consensus about how the spin is observed, basically by spin precession and cancellation of electrons with different wave vectors, which leads to spin dephasing. And you mentioned here that somehow you mentioned that physics is different in non-collinear antiferromagnets. So I'm wondering actually, how is the physical picture different from the ferromagnetic case when the spin current is observed into an antiferromagnet? I mean, the key question is, we inject angular momentum to the system, but where does the angular momentum go at the end? Because in antiferromagnet, there's no net magnetic moments. So to me, it seems a little bit confusing. Maybe could you clarify my concern?
Actually, so to be honest, I'm also confusing. So I recommend that you ask Kyunjin. And so I'm not sure. So I also have the same question with you. And so actually, my understanding is that the angular momentum conservation should hold true for all the systems. So
yes.
Yes. So I'm also confusing. But the result is here, and the 1/2 relation means that the angular momentum conservation holds true. Okay.
Okay, but absorption length until like 25 nanometer is very long compared to usual ferromagnet. Yeah, it's very interesting to me.
Yeah, me too. Yes, I also think so. Thank you.
Okay, thank you for your comments.
So I think there was another question from Mr. Midosh or something like that, but I think he's maybe has left now. I did unmute him, so Jun Young still has his hand up, but I guess that's from before. Does anyone else have a question or a comment? Yeah, Igor, now you can unmute yourself. Igor Sandarov, please go ahead.
Yeah,
we hear
you. Thank you for such a nice presentation. I have actually several questions, and first one is, I have feeling from your talk that you're discussing this material, this sample, as some molecular crystal. So your 6 atoms form some molecule, and then they interact between each other. And in your model, actually, it is not clear how material comes in, and if you also have shown data where response is different depending on the substrate, metal or insulator. You were talking about different materials, but nevertheless, in general, one is metal and another is insulator. And of course, there should be some experiment shows. Your experiment shows a different response. Question is, why? This different response I didn't catch from your talk. And the second is...
sorry, I couldn't catch the point of the first question. So could you...
First, all your speculations, it seems, are based on molecular crystal speculations. So you have manganese molecular, and you consider rotation of spin for this. It's actually not clear that this moment is sitting indeed in the plane, and where in your model interaction between these molecules, I didn't catch. You understand first question?
Sorry, Matthias, do you understand the question?
I'm also not sure, Igor. So just if you come back to the very beginning. So what do you mean by this? I mean, it's not a molecule. I mean, these are atoms
Yes,
in
of
a
course, it's
condensed
not
matter
molecular,
system.
but it's not molecular, but all these speculations which have been presented looks like main element is this molecule which consists of 6 manganese.
No, I think we're considering every single spin on the manganese atoms.
Yes,
it's
yes.
just a periodicity.
But question is inside of these 6 manganese atoms, if interaction is greater than interaction between different so-called molecular.
So you mean
then,
like so exchange interaction within
yes,
the 6 manganese and between 2 manganese of
other
different.
6 manganese, yeah.
I think this is known. I don't know, Dongwook, do you know the strength of the exchange integrals? Like, I'm sure this has been calculated.
Sorry, I don't know very well about the magnetic
the question
interactions.
is whether it is superparamagnet of
No,
this
no,
strange
no,
structure, or this is magnet. But this
no,
is
no,
magnet.
It's magnet.
The
the manganese of different kind of cells, they're strongly coupled.
Can I help?
So
yes, Helen, please jump in.
Because we studied, so we look at this manganese 3 stannum. This is a classical magnet with well-ordered magnetic sublattices, and the structure is well known due to the works of Japanese people. So this structure was studied in 60s, and there is no, it's not a molecular crystal in no way.
Okay.
So a strong exchange interaction which results in formation of 3 magnetic sublattices as shown, yeah, as in the slides.
Okay, so in the model, actually you have kind of mean field theory for these 3 sublattices, right?
Yes, exactly. So the model which was presented in this talk it is based on this macroscopic or micromagnetics or whatever. Yeah. Can you show this LLG equations which you used for modeling?
This one.
Yeah, this M are sublattice magnetization, and everything is known, angles, these constants, and so on.
Okay, great, great. Then second question was actually I am sure that here magnetic moment is sitting within the plane, or there is some small moment which sits out of plane, and then all the speculation have to be taken into account.
As far as I know, the magnetic moment is sitting in this plane.
There is small magnetic, so without magnetic fields, there is a small canting. There are 2 modifications of this phase 1 and phase 2. You show a configuration in which it could be some small canting within the plane. But there is also purely antiferromagnetic phase in this crystal. But it does not prevent the current-induced rotation. So the experiment is so accurate that you can forget about this in-plane tilting.
Okay, okay. And at last, this question about different substrate, metal and non-metal. Response is different. It was, I think, slide 26.
So 26. Okay. Yeah. So actually, we use the MgO substrate. So this is the order of the stack is that from the substrate side, tungsten, tantalum, manganese, tin, and platinum.
Yeah.
So this is the cap side.
Well, but it's sitting on manganese ore, and this is insulator. So this means that actually effective interaction between magnetic atom via substrate is very different. In platinum, you have conduction electrons, while in oxide you don't have them, which means that actually it's different systems. And
yes.
And question is whether it's a general thing sitting on metal or insulate or not.
So we use the same substrate, MgO. Okay. So MgO is here. So below,
okay.
Underneath the tungsten layer, right?
Yeah.
And the capping layers are different.
Yeah. That's what I mean. It doesn't matter if it's above or under, but question is whether effective interaction between these spins does exist. And if it does exist, then what is the contribution?
So I think maybe because we are running a little bit out of time, this is becoming very detailed. Maybe you just send a quick mail to Shunsuke. But I think it's well known that the exchange interaction within the antiferromagnet is very little affected by the capping layer. I think it's pretty identical. There's one more question from Kunrok John that he would like to be read out. So thank you for the nice and clear talk. For antiferromagnetic systems, T2, the spin dephasing time, can be much longer than that in ferromagnetic systems. I'm curious how T1, the spin relaxation time, differs between antiferromagnet and ferromagnetic systems. I think that a shorter timescale in the end limits the spin lifetime of spin currents in magnetic systems. So what is your take on T1 and T2?
Oh, okay. So interesting questions. And actually, that's a future issue. So we didn't evaluate T1 and T2. So.
And the second, how did you evaluate the actual current densities in the multi-layers? So what kind of interface resistances, and did you use Fuchs-Sontheimer, or how did you calculate?
That's this is the estimation is based on a very similar assumption that that each layer is parallel resistors. So we evaluate the conductivity or the resistivity of each layers, and from the parallel resistance model, we determine the current density flowing in each layer.
Okay, so parallel resistor model, but let's say the interface like interface resistivity is not taken into account.
We didn't consider the effect of the interface.
Okay, so any further questions? Otherwise, just one final. Can you just talk us again through the issue why you think that Joule heating is negligible in your experiment? You just say what is the argument? Why is no Joule heating effect visible?
Yeah, so we don't know, but if we apply much larger current, the temperature goes up to a few tens degrees Celsius, but the chiral spin rotation takes place much below the current at which the temperature goes up to.
So of course, Joule heating exists. Just change of resistance is small. That means change of temperature is small.
Yes.
Okay. Yeah. Okay. Good. All right. Good. So then, please everyone join me in thanking our speaker Shunsuke again.
Thank you.
Then we wish you a great evening, and I'll see you in about 10 hours, something like this from now.
Yeah. Okay.
All right. Thanks, Shunsuke. Bye-bye.
Thank you.
So thanks, everyone. We had 150 people today, so quite a good turnout for the summer season. So.
Yes, excuse me.
Yeah.
Can I ask you? You told that the effective interaction doesn't contribute much, but when you have current, then it's different thing.
No, it's just what I wanted to say is, what I want to say, the thickness of the manganese tin is relatively large. It's like 8 nanometers or something like this. So therefore, change of the top one monolayer is not so big for total exchange interaction, my experience.
Yes.
So maybe some interface anisotropy play a role, but exchange interaction, average exchange interaction is very little affected by capping layer.
You know
for this thickness, if you make it much thinner, yes, of course, interface becomes more important.
But it's known in semiconductor that induced magnetization arises when you excite electrons over the gap.
I mean, there are many things can happen. I just wanted to say that, for instance, there's negligible change of Néel temperature with capping layer. indicating that there is no significant change of exchange.
Okay.
So I'm not saying it's impossible. I'm just saying that in this case, it's not very important. Okay, everyone. So thank you. Thanks a lot.
Okay.
And yeah, thanks Shunsuke again, and I'll see you later.
Okay.
Bye bye. Matane.
Bye.
Arigato.